Welcome to Engineering Innovations, the official podcast of Purdue University's Elmore Family School of Electrical and Computer Engineering. I'm your host, Kristin Malavenda. Today we're exploring a topic that affects everything from streaming your favorite shows to the future of artificial intelligence, visual data compression. How do we make images and videos smaller without losing quality? And how does AI both help and complicate that process? Joining me is Purdue ECE professor Maggie. She studies how artificial intelligence can make image and video files more efficient, helping us store, send, and process visual data faster and with less energy. Her work explores three big questions. How can AI improve compression? How can we design compression for machines instead of people? And how we can even shrink the AI models themselves to make them run more efficiently. Maggie, thanks so much for joining me today.
Well, thank you, Kristin, for the opportunity to talk about my research.
Yes, I'm sure AI is all over, so this will be a very interesting conversation. So for listeners who aren't engineers, including myself, can you explain what visual data compression is and why it matters in our everyday lives?
Yes, so visual data here in general are referring to images and videos, of course, and then they're made of pixels, which is short for picture element.
Okay.
And then this, is a digital version of how we capture, the actual physical world, using our CCD sensors, cameras and so on. Okay, but it can also refer to other type of more specialized data like hyperspectral imagings, even like point clouds and etc. And in fact, that images or videos are the main source of the new type of data that are living on the internet now. Okay, so for example, if you open up your smartphone, I'm sure one of your favorite apps has something to do, with images or videos,
yep.
Right? But however, they take up a lot of space, okay, to store them, to send them, and just because of the sheer volume of them now exist, on the internet, we need to do something about it. Okay, so image and video compression in general is the process of how we can reduce the file sizes by remove redundant information in these file format, and the information we wanted to remove are essentially less critical to the image's overall quality. And I'll say a little bit more about this later.
Okay.
So at a very high level, to do this, we have what's known as an encoder. So it transforms these pixels into a more efficient binary representations. Okay, yep. And then we put them, store them on hard drives, or we can, send them through the internet. Okay, then at the decoder side or the receiver side, then we have a decoder that essentially unpacks these bit streams to reconstruct the pixels back into their original forms of images or videos.
That reminds me, I don't know, did you ever see the movie Charlie and the Chocolate Factory?
Yes.
And the scene where he's sending the chocolate bar and it goes and the things fly over his head? That's kind of what it makes me think of.
Yeah, that's a really good analogy to what I just talked about.
We're all used to seeing file types like JPEG, paying formats like HEVC. How are these traditional approaches different from the AI-based methods that you're studying now?
Yeah, so these file formats are the result of specific algorithms that are known as lossy compression. Okay, and what lossy compression does is that it permanently removes some information from these image and video data, and the goal is then we can achieve a smaller file size. Okay, now while these methods can reduce the file sizes significantly, sometimes even up to 90%.
Oh, wow.
Okay, yeah. But there is, of course, a price to pay for it, which is, this loss of quality. And, it may not be noticeable to human eyes to some extent, depending on how much is being removed. Okay, so this trade-off is known as the ray distortion. Okay, and this is kind of the core of how we design compression algorithms.
Okay.
And so the rate kind of refers to the amount of bits, since we're talking about binary data, that are required to represent these compressed versions of the image and videos. Okay, so you can see that a lower bit rate would means that we have a smaller file size, and then we have higher compression efficiency.
Gotcha.
Okay, so on the other hand, we also have something known as distortion. So as the name means that it's a measure of how much loss is this quality. Okay, so then the objective we have is how do we find this best balance between these two sort of competing goals. Okay, so traditional methods, as you mentioned, like JPEG and the HEVC, they're known as transform or hybrid based coding. Okay. And they achieve this balance through a set of these predefined, quite complex tunable parameters.
Okay.
Now, because of these fixed nature of these parameters, it sort of limits the flexibility of these methods to adapt to, perhaps varying contents of the images and videos. Okay, so it constrains their overall efficiency. So recent advances in sort of learning-based methods, so learned image compression or video compression, also rely on this, ray distortion optimization. Okay, but it utilizes deep neural networks, right? AI tools, to essentially automatically adapt to the data that it's, using, and it learns these very intricate feature representations that are directly from the data, so it can sort of achieve better or higher compression ratios while still remain sort of these enhanced qualities at the end.
Gotcha. So why has the rise of AI created new challenges and also new opportunities in the way we think about compression?
Yeah, that's a very good question. So as you know, we live in an era with increased data traffics. Okay, and then these are mainly videos on data, so we have more video content, right? And obviously we have increased viewing times from our users. We have higher resolutions and more like demanding format, like high dynamic range images, right? And then we also have emerging applications. For example, AI generated content, right? For example, short form videos that are everywhere. There are real applications. There are AR, VR applications, right? And there's a huge cost associated with the storage and transmissions of these data. And then we also have to think about these environmental, economic factors that are playing the role, right? So, if you think about traditional, these hybrid based, coding standards and then, formats, they're still really the workforce of in today's systems and devices. So if you look at, how, we're using or compressing our data now, it's still relying on those formats, okay? But the margin of performance gain for each of these new generations are getting, extremely small with, the kind of the trade-off of having increased complexity.
Right.
Okay. So what AI-based solution are offering now is, yes, it's still at its infancy, right? And it faces, many challenges, which, I can talk a little bit more about it, but, things like higher, energy consumptions, there's, hardware sort of compatibility, etc. But it does show a lot of promises to support not just, existing image video formats that we have, but also sort of enabling, emerging applications that we may have in the future.
Gotcha. So you said that sometimes we design compression for machines instead of people. What does that mean, and what are some examples?
Yeah, so while sort of much of what I just previously described, content, particularly like video contents, are directed at human viewers, viewer consumptions, right? So, but there's also a rapid expansion of applications or even user cases that the human eye is never going to see it. Okay, so it's never going to see the content, and where machines or algorithms are the actual intended consumer. Okay. So let me give you a more concrete example. Okay, so imagine that we have a next generation factory assembly line. Okay, and it contains several video sensors that essentially, I would say, quote unquote, watches. Okay, so it watches the items that's passing by the assembly lines, and then the video feeds will be sent to some centralized analysis unit, and then it may stop the assembly line when some unauthorized object that showed up and observed on the line. Okay, so these very sort of detailed and complex operations can all be processed without any human ever seeing it. So there's no human interventions at all, right? Okay. And also, I looked this up the other day. So the number of video surveillance, cameras or these sensors are expected to reach 1 billion. Okay, by the end of 2026. Crazy. Yes. So, and also to sort of further bolster this trend, we have this increasingly successful AI algorithms, right? And these models that they can solve even more complex the vision and perception tasks, like detecting objects and then tracking, and then they're sort of performing at near human levels or even surpassing human levels, right? And then you have add on to that these widespread deployment of these sensors that are capable of capturing and transmitting video streams, like our home security cameras, right? Like factory automation sensors and all these IoT devices. Okay. Now, so one issue with these sort of more low-cost devices is that they don't really have the compute resources or even the battery capacities to run these complex AI models and algorithms that are required by these vision tasks. Okay, so these operations are typically better suited to run in edge computing servers or even like cloud environments. Okay. So now in this sort of growing ecosystem that we just talked about, there is a need for sort of new compression mechanisms. Okay. And a critical consideration of these algorithms is that what machine sees and what human eye observes are very different things, as you can imagine, right? So for in this assembly line example I gave, you can think of these vision tasks are only sort of needs these parts of a frame or an image from the video that informs whether the object being detected has unusual shapes or dimensions or geometry, but the rest of the frame, it doesn't really care of what it has, right? But versus for human eyes, we need this contextual information for the interpretation, right? So and also, by discarding sort of these ancillary and human-specific informations, then we would need, far fewer bits, for, be able to support these successful deployment or execution of the vision tasks. Okay, so a good compression algorithm in this case, will be key to allow machine visions to carry out and support this demand for the bandwidth.
So with so much of this data being processed on mobile devices and in the cloud, does compression make those systems faster or more efficient?
Yeah, so I would say yes. And then, with the kind of particular examples that we mentioned earlier, so currently, I would say there are sort of two different approaches to address these challenges. So one is that, we can sort of fully offload all these vision tasks, like when the sensor device encodes and transmits videos to, remote servers for processing, right? And then, but here we still, need efficient algorithms to do this to handle the large, amount of data. And a second approach is something that our group also has been actively working on, is to sort of split this vision kind of models into two parts. Okay, so you have one part that are at the sensor device, where and then you have another part sort of runs on a remote server. Okay, so this sort of we call these split inference architecture. So it involves only transmitting these intermediate features that the vision task will be need for further processing on the cloud. Okay, but in both cases, we need efficient compression and transmission of the data, right, from the sensor devices to the remote server. And then I think this is very crucial for building, a viable sort of network-assisted computer vision applications.
So we mentioned neural networks, and they can be very large and resource intensive. So what does it mean to compress an AI model? How do techniques such as pruning and quantization help that process?
Yeah, so model compression kind of refers to the process of how do we reduce the size and the computational requirement of either training or inferencing these machine learning models, right? And then particularly for deep neural networks, but we want to do this without kind of significantly compromising the performance or the accuracy.
Right.
Okay, so this is achieved through techniques, as you mentioned, like quantization, right? So essentially it lowers the precision of the model numbers, and the pruning is to remove any redundant parameters. Okay, so the primary goal here is that, how do we do this so that we can enable deployment on resource-constrained hardwares, right? So such as these edge IoT devices, and improve, inference speed as well as the energy efficient. Okay, so there's another aspect of this, particularly with these rapid evolutions of large language and the vision models, okay, because they have, as we see, that essentially revolutionized AI further, and then many applications comes with it. Okay, but despite that, these remarkable performance they're able to achieve, they incur sort of prohibitive, computational memories and storage cost, right? And during both training and inference, right? So for efficient data compression, that it is sort of emerging as more of a critical enabler to essentially scaling, these models, because we'll talk about how do we scale this, right? So scaling these models so that we can have more broader deployment, for different scenarios, and especially in these resource constrained devices and then or cloud edge-based collaborative environment.
So we keep talking about these how to build and process these AI-driven compression systems. How will that change industries like healthcare or entertainment or autonomous systems? What's the impact of that?
Yeah, it's I like how we're talking about applications. Yes, so I think for all of these there's tremendous amount of opportunities. So I'll give you some examples, right? So in healthcare, I think the implication is very profound. So we know medical imagings, right? Things like MRIs, CT scans, X-rays, and so on. They actually produce massive amount of files. Okay. So if we have faster transmissions, then we can facilitate sort of quick second opinions, or even for remote consultations in rural areas. Right. And we can also have more efficient storages for all these, maintaining these very comprehensive digital patient records.
Right.
Okay, so that's also a very big thing. So other benefit could be in more enhanced AI diagnostics, right?
Okay.
To accelerate the training and deployment of these AI models to do this for disease detection, etc. And I think related to my earlier comments is that I think in telemedicine, when we have higher qualities of videos and then data streams for remote surgeries or even consultations, that I think will require a lot of reliabilities, accessibilities, even with these limited bandwidth. So this is where I think compression will need to kind of play a really crucial role for that. And speaking of entertainment, we always want higher quality streamings with less bandwidth, and then especially with all these VR AR applications, we want to enhance the user experience.
Less
we want to reduce the latency, right, and smooth experience and more immersive, right. So a lot of these 3D kind of virtual environment, this. Because our human uses a lot of sensory cues, right? So when something is off, you really kind of can tell, right? So how do you enable the immersiveness and then less hardware constraints? Okay, and I think lastly, for autonomous systems, and then these can include self-driving cars, drones, robots, right? And then they rely heavily on real-time processing, okay, of the data. And from different sensors. Okay, so for example, if you think about AI-driven compressions, I think it's a really game changer here. So these real-time sensors that do data processing, and they are producing terabytes of data per hour. Okay, from different cameras, lidars, radars, ultrasonic sensor, you name it, right? So we need more efficient data compression so that we can achieve more remote monitorings, provide even more extended range, and then for drones and robots, and even for I think fleet management, I think it will provide more efficiency to that. So in essence, I think this AI-driven compression is not just about how we make the file smaller, but it's really about locking new possibilities, right, for these data-intensive application across different industries. And then so the goal is that we want to have greater efficiency. We wanted to have reduced cost, but we also want to enhance this user experience, whatever the user is at the end of the line. So
can I ask you a question? What led you to this research?
It's an interesting question. Yeah. So as you probably know, I received all 3 of my degrees, bachelor, master, and PhD from Purdue. So when I first took EC undergrad course, so this is EC 301, it's the signal and system course, and it was taught by one of our very great faculties who is not here anymore. Mm-hmm. But this has really stirred my interest in to see how beautiful and then its simplicity of the signal and the processing of the signal, right? There's beautiful math and theory behind it, but it's also so powerful to be able to solve all these different type of applications. So this is really kind of stirred my interest and wanted to know and then learn more about it.
Oh, great. Thank you. So looking ahead, what do you see as the most exciting possibilities or maybe even the biggest challenges for visual data compression in the AI area?
Yeah, so as I mentioned earlier that, we're still at the infancy, of this new technology. Yep. And so as you can imagine, how do we ensure consistencies across different platforms, right? That we have, consistent output for diverse hardware, that's very challenging. And then also the energy consumption aspect is still there because we rely on, models that has a lot of parameters, right? And then, different, I think, than traditional compression methods, which go through very rigorous process of standardizations and then developing protocols so that the manufacturers of these hardware devices, they know like how do I build or pack my bit streams and all that, right? So there is ongoing work related to that, but it's still again we're still kind of lack that standardization of more formal AI friendly hardwares, which is limiting some adaptations. Okay. And lastly, I think some of these AI-based compression methods do rely on generative models, right? So as we know that these generative models may introduce hallucinated content, okay, that are not faithful to the original images or videos that are looking, right? So this could raise some kind of concerns in sensitive applications that rely on good securities and trust. Gotcha. So those are, I think, some of the challenges that the researchers are working on now.
When you went through your 3 degrees here at Purdue, did you always know you were going to be a professor, or what led you to teaching as opposed to industry?
Yeah, so I did originally work in industry for a few years, but I always know that I want to work on research. I just wasn't sure whether I want to take an industry path or in academia, and then so I wanted to see, because I like to solve. I'm an engineer, by heart, so I wanted to solve real problems, and I want to kind of see the product that as a result of this. So that's why I went on industry, and I was in the research lab. So we kind of do the usual industry research, but also we have another feet sort of another foot in kind of publications and all that. So it's sort of I think a nice intermediate step. And then opportunity came, and I feel like I wanted to have more sort of freedom to pursue longer term research. And then this is something oftentimes I think industry is difficult to offer, right? So even when we have 3-year, 5-year plans, we end up have something we have to deliver in 6 months or in a year, right? So and then
it's all connected to what they want to spend the money on too.
Exactly. So you don't have sort of the autonomy to control what your passion is, what you want to work on. And then I think the other aspect is I didn't know how much I enjoyed working with students and mentoring them, and then so that really has becoming kind of my motivation, to get up and then every day, and then to enable them and see like how they go from someone who have the knowledge but don't really know about research and becoming great researchers independent scholars. So that's a very satisfying part of the job.
Yeah, I assume when you're working with students, a lot of what they do ends up in, they would think of it as a failure, but it's really just kind of a jumping off point to do something else. How do you help your students understand that just because it didn't work out doesn't mean that's a bad thing?
Yeah, so I think one of the biggest sort of mindset change that I see with a lot of our undergrad students, going into grad school, is this concept of there is the correct answer.
Yeah.
Right. So I think once they realize, oh, there is no correct answer. Oh, my professor may not know the correct answer, and I told them that's why we're working on the problem, and we're going to find these together. And there's roadblocks, and I think going to graduate school, particularly pursuing a PhD degree, is not just getting the degree so you can put that 3 letters behind your name, right? And then or open many doors, of course, but also I think it's a life skill training. So you sort of have these life skill, the mindset of how do I deal with just hard problems in life.
Right.
And then, so I think that's a very, very valuable lessons. And then because of the time that it takes that for you to become really the expert in the topic, maybe it's it's a small topic you're pushing, the whole research field, but you're still the one, you're going to be the expert. So oftentimes I tell my student, by the time you graduate, you should know a lot more about this specific topic than your professor does.
Oh, that's interesting. I like that. So you did all your degrees at Purdue, and you came back to Purdue to teach. So there's something about Purdue that you enjoy. What makes Purdue the place that is good for you to teach and do research?
Yeah, so I think I've sort of witnessed the kind of the expansions, I would say, with the department, with the schools, and then I think what hasn't changed is over the years is the faculties we have. And then the support system we have, that, when you talk about Purdue with other people, and then we have a lot of friends and colleagues who are successful in industry, they always know, yes, Purdue engineering, it's like, it's up there, right? It's the top. And then we do solid work. And then because of, and then a lot of the projects, including what I do in PhD and now, are very collaborative in nature. Right. So being at a school where you have all kind of opportunities, and then you have people who can say, hey, do you want to, be on this big project? We need someone who are an expert in, working with images and videos and so on. Then they can find a person, and then I can find, oh, there's a problem that, we can apply our expertise into. So I think that's, and then I think just the mindset of we are engineers, and then we wanted to solve problems, and we wanted to make impact into real world problems. And then so that's, I think, something very unique to Purdue. And then that's, we strive, for excellence.
That's great. So you spend a lot of time obviously teaching, researching. When you do get some free time, what do you do to decompress and relax a little?
Oh, so I do wear a different hat on a daily basis.
Okay.
So I am, mother to our kids too, right? So, spending time with family, going to kids' activities, that, takes most of my other time outside of work. But if I'm lucky to have some personal time, I do enjoy reading a lot. But nowadays, like listening to audiobooks.
Yeah, I've been doing
my
that a lot
eyes
more
get,
too.
a break. And, I enjoy music. I play the piano, and then, trying on new recipes in our kitchen. So.
Yeah, great. Well, thanks so much for taking the time to talk to me today.
Well, thank you, Kristin, for the invitation.
And we talked some about the environmental impact of AI today. If you want more information about that, you can listen to the podcast with Professor Yi Ding, which was last month. So if you enjoyed today's conversation, make sure to subscribe to Engineering Innovations wherever you get your podcasts. And if you like what you heard, please rate the show and share it with a friend or colleague. It's one of the best ways to help others discover the groundbreaking research happening here at Purdue ECE. You can also follow Purdue ECE on social media to stay up to date on our latest stories and discoveries. You'll find the links to those platforms in the show notes. Thanks for listening, and be sure to join us next month for more stories of discovery and innovation.